Hello, everybody. This is Bernhard Mickel from Himba Photonic. In this video, I would like to talk about Straylight analysis using our software RayJack ONE. It's quite a long video because there is simply so much to talk about. Let me first start with Himba Photonic, which is a very small engineering company in Germany. These are our employees. Only one is missing on this picture. And we offer optical design and analysis services, including applications that have to do with light scattering, such as this optical particle sizer, the non-imaging optics, which means sensor and illumination optics, and our specialty here is Straylight analysis, where our main customers come from space industry. But we also offer optical software. Its name is RayJack ONE for doing non-imaging optics and Straylight analysis. And the software development was funded by the European Space Agency. This talk is a sort of synthesis. It brings together, on one side, our engineering and physics know-how. On the other side, our optical software, non-sequential optical analysis software, RayJack ONE. And you need both to do Straylight analysis. So you need experienced optical engineers and you need a capable software tool. Otherwise, it simply won't work. In this talk, I would like to talk about Straylight analysis and Straylight in general, introduce a little bit to RayJack ONE, then I'll give a quite extensive software demo about Straylight. And then I switch back to this presentation and go through the different Straylight contributors, discuss Straylight analysis strategies, and finally draw some conclusions. Now, when you design an optical instrument, such as this UV lens here, you normally adjust the system parameters, such as the shapes of the lenses, such that the so-called nominal light is optimized. In this case here, for instance, you have a very sharp spot. Straylight, however, is unwanted light entering an optical system as opposed to this nominal light. So when you look here, you see that some of the light hits actually the edge of this lens and produces a signal here, which is unwanted. And generally, this Straylight can severely degrade system performance by reducing the image quality. That means contrast, resolution, or in one word, MTF. It increases measurement noise. In laser systems, it may damage optomechanical components. In illumination systems, it may lead to glare. And so it can be quite harmful. Now, Straylight analysis is the quantitative prediction of Straylight of a virtual prototype. So it always happens on a computer, which is very important to note. And its second justification is that it is needed to identify Straylight causes and paths in order to reduce Straylight in the system. What's the benefit of Straylight analysis? First of all, it gives you an in-depth understanding of an optical system, and typically from an external perspective. So when we take over a Straylight analysis, we are not the optical designers, and therefore are more or less impartial when evaluating the system. And actually, you should do it as well when you and look that if you're doing a Straylight analysis, that maybe another optical engineer, not the optical designer, performs this analysis. Then it helps you identify the potential for optimization. It has many advantages over experiment. Although at the end you will need the experiment, it's less expensive because you essentially can do everything on the computer. It is possibly early development stages. That's very important. So even before a hardware prototype is available. And you can look into the system just like when you use X-rays. You can decompose the total Straylight into partial processes, which is very important for understanding. And you can simulate scenes that are difficult to make in laboratory experiments. Mostly because of these early stage studies, it is an extremely important de-risk strategy to avoid project delays and, in the worst case, project break-offs. So in the past 15 years, we had 2 break-offs, and one of them was really catastrophic. Once you have a Straylight assessment of your system, it adds value to your product. Yeah, because your customer can see that you really have taken care about that. And finally, that's coming more and more when Straylight results are quantitative, you can use them later on for image correction. Now, where to start? Let me first compare optical design and optical analysis software. So optical design software, typically for imaging optics, is mostly based on sequential ray tracing. It uses rather simple physics, essentially the laws of reflection and refraction. But that makes these software products very strong. They have a powerful optimizer to modify the position and shape of the optical components until they meet system specifications. Normally, they only care about nominal light. So, you know, several of these software products like Optic Studio, Code 5, Oslo. Here I would like to mention Synopsys, which is an excellent software by Optical System Design in USA. Now, optical analysis is quite different. It is based on non-sequential ray tracing. It models the non-ideal behavior of optical systems. It has to cope with a multitude of physical effects. It has to take input data from many different sources. For instance, the lens, this is from the lens design software. You have to import CAD models. You need CAD because now, obviously, the mechanical parts of your optics can also interact with light. Scattering data from databases and many other different data. And furthermore, it's very typical that there is a quite complex data analysis required. And it's mostly non-standard. So for each project, you have to analyze differently. So Straylight analysis definitely requires optical analysis software. Now, how to do it best? So, yeah, 11 years ago, we made a publication where we tried to couple ray tracers with self-written software in order to do this analysis in Python, which was most used then. For the ray tracing, we used at that time CMAX or ASAP. but we always found shortcomings in you could not access all data, so that it was rather inconvenient to do that. The second alternative is to write a software which is completely inside Python. And RayJack ONE is such software. It is a non-sequential ray tracer integrated with Python so that you can do everything. The ray tracing and all the analysis within one environment, making it very, very efficient to work with that software. A bit about the history of that software. So we first use it as an in-house non-sequential ray tracer. And the first prototype, which is worth calling it prototype, was then released in 2017. And the European Space Agency got interested in our development and funded it because of the specific needs of such software for space industry. It's on the market since late 2019, first with limited functionality, but since roughly 2 years, it has the full functionality, has passed the ESA final review, and in the last 2 years now, it was used intensively by our customers and by ourselves. And it turned out that this is a really exposure to real world problems has pushed the quality of the software forward so that we now can rely on its results. And it's getting more and more streamlined now for practical applications. Now let me switch to a live demo of the software, and as I told you, I will concentrate on Straylight. I won't talk about other things which already have been covered by in other YouTube videos. So when I start with a new project, I open the script editor, and let me start here with a basic analysis script. And very similar to what I've already shown in other videos, I will create a simple lens as a starting point, and lenses are objects in Python, just like everything. I create a singlet from its paraxel data. Let's call it lens. And you have seen that in other videos. Here I put the alignment in, the position. On axis, it's thickness at the center, it's semi-diameter. Let's take 12.5 millimeters. For the focal length, I choose 70 millimeters. And the bending factor, just more or less arbitrarily, 0.3. For the wavelength, this is the design wavelength for which the paraxial focal length is computed. I take 550 nanometers, and for the glass, I go here to the glass library and take standard shot NBK7. So now let me continue right away and add a detector at, say, roughly the position of the focal point. And here, let's make it a little bit larger. So, and finally, let me add a light source. I'll take a Lambertian light source, and if this is done this way, we call it LED. Position it slightly in front of the lens. Let me restrict the here I specified its aperture. Let me use a quite large LED with a maximum angle restricted to 45 degrees. And for the number of rails, let me use 200 or something like that. The wavelength, here I just pick one, the same as before. I could also assign a spectrum. Now this is my optical system. I can readily trace and show it. And it's a little bit boring. So we have our LED, the LED light passing through the lens. And obviously this is a really bad design. So only a few of the rays will hit the detector. But that's intentional because I would like to study Straylight. Let me now go a little bit further with by adding to this example a mirror. Now, a mirror is a plane. It's all surfaces we call, that have physical properties. We call it physical object. And we rotate it by 45 degrees. Now, placing this mirror, the detector would not receive any light anymore. So we therefore rotate the detector about the mirror, but we will still mark here the original position of the detector, because it turns out that this is exactly the virtual image of the detector in the mirror. Now let me simply trace this, and now you see I also rotated the LED a little bit to make things even worse. Now, this is the detector, as I told you, rotated about the mirror. And here, that was the original position, which is exactly the virtual image of the detector inside the mirror. Now, let me go one step further and assign scattering to the system. So in order to do that, now let me first start with a back side of the lens. So for this, I create an object, a BSDF object, and let me just run this alone. So the BSDF for roughness, that's very typical, has such a very pronounced peak in a forward direction. It's very rough, this lens, just to show the effects. And with this command, so that's the lens, the backside, scatter, I assign scatter properties. Scatter transmitting, that means light shall be transmitted, and I create secondary rays, namely 10 for each initial ray. Let's see what happens. And you see, well, scattered light goes in all directions, and for more complex systems, you will find out that finally, possibly not a single ray or only extremely few rays will hit the detector. So this is very inefficient to do that. The standard trick for improving statistics is that you perform importance sampling. Now, this means that the rays are restricted to directions that are relevant for the analysis. When I scatter here from this lens, when I restrict scattering to rays going towards the virtual image of the detector, then the mirror will deflect them just in the right way so that they will hit the detector. Let me do that here by just changing that. Now here I have assigned a target to my scattering, and you will see that now really the rays are produced that will be guided towards the detector. Let me go one step further and also add scattering to the mirror. In this case, the rays will be ray directions will be restricted to the direction of the detector, and I also now allow for more than up to 2 splits of the rays at lens surfaces. So when a ray hits a surface, a part of it will be transmitted. The part, normally the weaker part, will be reflected. And this, so 2 rays will be generated. And this reflected ray may split a second time, then the higher orders will be suppressed, so that it can change its direction twice. This is the way normally one models ghosts. I will get back to that in a minute. Now let's run everything, and you see now that a lot is going on, but you cannot really understand details here. Everything is black, and therefore in one simple step towards getting a little bit more insight into the system is to color the rays. So here I color all rays that have been split once with blue, twice in lavender, all rays scattered from the lens back in red, from the mirror in orange, and here I have marked the rays that have hit only one object and end on the screen, and they are colored brown. So this is the rays bypassing the lens. Also, I should mention that it was a little bit oversimplified what I've shown before. The lens backside cannot only scatter towards the virtual image of the detector, it can scatter directly towards the screen. So there are systematic ways to find that out, and I will get back to that later. Now you see a picture with much more information. Let me remove all rays and switch them on again. So let me make the blue rays now visible. These are the reflections from the lens, from the front or the back side. You can show the rays that have been split twice. So these are the ghosts. They go back and forth inside the lens, and some of them make it to the detector. Let me here mark the rays scattered from the mirror, and finally rays that have bypassed the lens completely. I also computed the irradiance with a very, very low resolution. So here I could go to some linear scale, a logarithmic scale to see a little bit more. So there's actually quite a bit going on the detector. If I want to see where a specific ray comes from, I can click here and make a hotspot analysis, and you see in this case it's light possibly scattered from the lens and light via the mirror and directly scattered light. I can also get more information about these rays when looking at my path table. I won't have the time to go through that, but just let me mention that here you get the rays sorted with different, according to different categories. For instance, the number of splits, the number of scattering events, total internal reflections, and here the path they have gone in the system, and you can use this information to make a detailed analysis, show the paths, compute the irradiances, and so on. Now, for computing the irradiance, you should, of course, use more rays. I did that before. And then when you do that, this took 1 or 2 minutes, then you can really get all contributions on the detector separated with respect to the process that generated them. So scattered at mirror, bypassing light, nominal light, and so let me go back here to this picture. Here you saw that the double split rays, the ghost rays, they really hit only part of the detector, which was, it can also be seen here in this simulation. So that's all for the moment. Let me now switch back to the presentation, and let me give you an overview over Straylight. So one component of Straylight is direct non-nominal light. This is light, in our case, it was the light that bypassed the lens, and it occurs just too often in optical systems. That we already learned a little bit about the ghosts. Then scattering from optics and mechanics. Here we talked only about scattering from the optical parts. But there are more contributions like out-of-band light when you're analyzing spectrometers, self-emission, which is very important when you're analyzing infrared systems, and more exotic things like wide-angle diffraction. All these grayed out contributions will not be covered in this talk. And of course, there may be combinations of these effects. Let me pass to the non-nominal direct light. Here's an example of a mirror system. And here we have the primary mirror, and here we have the secondary mirror. And in this case, we found that when we start from the detector, not all rays sent out from the detector will really hit the secondary mirror. Some of them will bypass them. And this will create severe problems, of course, in the optical system. Unfortunately, such problems with direct light occur almost always with mirror systems. And the explanation I have is that the optical designers only care for nominal light, and they do not even look at such effects. So in this case, the solution is simple. You place a baffle around it, and then things are done. The first thing you should do in a Straylight analysis, look for this non-nominal direct light. Ghosts are non-nominal reflections from optical surfaces, typically from lenses, and through two reflections, typically they may reach the image plane. Other components we also contribute to ghosts. And you see, one of the problems for ghosts is that they may create hotspots, so that they can be quite serious. So here, this simulation was done with differential ray tracing, which is a unique feature of RayJack ONE, but in many other cases, it's simply do it as I've shown in my example. Now, how to reduce ghosts? So one thing is to have a better anti-reflective coatings. In this case, I should note that once you have done a simulation and store the data, it's often possible to compute the effect of a different anti-reflective coating just by rescaling the results. You may place additional baffles. In order to do that, you have to compute the footprint of the nominal light. Then you have to compute the footprint of the ghost light, and the baffles should be placed such that they do not interfere with the nominal light and block as much as possible ghost light. So, of course, this is also supported in RayJack ONE. Another trick is to tilt optical components, which very often works if the components are far apart from each other. The worst case is to redesign the optics to eliminate hotspots. Then you may think of off-axis optics in this example, so that you just cut out the relevant parts of the lens. And you may use reflective optics, because mirrors normally don't produce ghosts. Ghosts may be aesthetic, like here for this cinema lens, where we intentionally created this flare, which in true color representation will be bright blue. In systems like laser systems, where the lenses are far apart, you will often find out that most of the light that gets reflected will be reflected outside the optical path. And so that the statistics inside will be extremely poor. So you may need millions, hundreds of millions of ray to get sufficient statistics. We have designed a method which is based on the so-called pathfinder. So we send out the rays. The rays, when they are successful with finding the next object, there will be more rays sent out into the vicinity of that ray, and so on until it reaches the detector, and then it is able to scan the detector with high accuracy, so that you get ghost results without any noise, which you can even use for coherent ghost analysis. Now let's talk about light scattering from mechanics. So this is a double Gauss lens with the aperture here, aperture stop, and light may scatter from the inside of this aperture stop. Let me mention here that once again, you may run into noise issues. So here you should take more rays, and typically you need to do importance sampling, as I have explained before. When light scattering from mechanics takes place, it is often the dominant Straylight contribution, so that you really should have an eye on it. So scattering from surfaces characterized by the BSDF. The typical measurement setup is shown here. You shine in at one angle and detect the light at different angles. So you need to have models for this BSDF, and typically you take them from databases or from bits to measure data. So here is a typical result for MAP, a black paint. And what you see here is this is this magenta curve is the scattering in all directions when the light is incident perpendicularly. So it's rather flat and has a quite low value. But as soon as you go to higher and higher angles of incidence, scattering goes up dramatically. And so that's has one consequence. When you're doing mechanical design, always have a look that there is no grazing incidence of light. So this is something very typical for almost all paints. There are others, not only MAP, there's Nextel Black, Actar is very famous, Vanta Black, Aeroglaze, Electroduct, MAP, Kepler coated, many others. When you want to block light scattering from mechanics, there are in principle 4 methods to do it. One is, suppose here we have the light source, we have the scattering objects and the detector, then you can place something in between, so you block the stray light. Then you can try to turn away your scattering objects so that it doesn't receive light anymore from the source. You can turn it towards the light source in a way that the scattered light cannot reach the detector anymore. And finally, you can blacken the surface. Now, quite generally, geometrical methods are much superior. So try everything possible to find geometrical tricks to block the stray light. This way you can reduce it often by many orders of magnitude, whereas taking a blacker paint that you already are using gives you at best maybe a factor 10. Now, when looking at optical surfaces, there are 2 effects. One is roughness, and the other, which is unavoidable due to the polishing process, and typically leads to a very pronounced peak in scattering. The same is true with this peak with contamination. So when particles are on the surface, they also will produce such a peak. Both create a sort of halo around the nominal light and can be quite harmful in optical systems. Often stray light is driven by this effect. The avoidance and reduction can be achieved by better and cleaner surfaces, which may cost quite a bit. Finally, when you're bringing things together, you also will have to cope with multiple scattering. Very often single scattering is dominant, but not always. And then you have to cope with multiple scattering, like here inside this baffle. So light goes back and forth, and RayJack ONE offers a feature, so-called observation rays, with which you still can compute the signal on the detector quite accurately with a reasonable amount of rays. Let's talk about the simulation of stray light. So you may ask whether it is better to trace the rays forward, that means from the light source to the detector, or maybe you do it the other way around, from here to here. This is both possible from a radiometrical point of view, and you only have to decide which direction gives you the better statistics. So in this case, when you have a small source and a large detector, I would definitely trace from the source, because many rays will hit the detector. Doing it the different way, if you trace here from the detector, only very few rays will hit the source, so it's a bad choice. Now, suppose that this is the source and this is the detector, then of course you would trace from the detector, because still many of the rays would hit the detector. So it's a matter of statistics, and quite generally for self-emission problems in infrared, you take the way that you trace from the detector towards the source. This is just a small verification that both will work. Now, the strategy in Straylight analysis is first that you try to find out which objects receive light. So they have to be considered carefully then. These are the so-called illuminated objects, and they are determined by forward ray tracing, so from the light source into the system. And more important actually are the so-called critical objects. These are objects that can be seen from the detector directly or indirectly through intermediate optical components. They are determined by backward ray tracing, of course, because I really interesting what can be reach the detector. If these critical objects are illuminated objects at the same time, then single scattering may already create a signal on the detector, which is typically very harmful. So watch out for objects that are critical and illuminated at the same time. Normally, when we do that, we do not only save the critical object, but also the last but one object hit. If we look at this mechanical part, it will then be maybe this one. The last but one object will be a lens, and we need that later on for computing importance sampling, which will be discussed here. So quite typically when you're trying to do a brute force approach to model light scattering, it won't work. There are only rare cases where this is different. So, and there may be cases where you would have to spend thousands of years actually to get a good statistics. So therefore, there is no way around the importance sampling. And the typical trick to do that is that consider here this case, a lens, scattering object, and a detector, that you compute the image of the detector, in this case, the virtual image of the detector, and direct the light towards this virtual image. Then by refraction through the lens, it will be directed exactly towards the detector. There are other tricks which can be used, and we have built in to RayJack ONE, so-called automatic importance sampling tool, where you can compute this importance sampling. It's quite some work if you do it manually, but also provide alternatives in case if that the statistics of these targets is not good enough. So this requires some inspection after the software has made some suggestions to you, but it's a very powerful trick. Let me talk a little bit about the typical strategy, the overall strategy of Straylight analysis. First of all, we will do a ghost analysis, and it's typically done separately from the scattered light analysis. We will use normal ray tracing or differential ray tracing depending on the application. Then we look at single scattering. We determine the critical and illuminated objects. The critical ones are the more important ones. Then we compute the targets for importance sampling using this automatic tool. Then we have to assign scatter models and targets to the components and start ray tracing. And multiple scattering, as I've shown, can be either decomposed into single scattering events, which is quite, it time consuming, or you can use the tool just described. Things can be much more complicated if combinations of ghosts and scatter need to be studied. I will skip that. It's can be quite hard to do it. Now, in practice, when you perform a Straylight analysis, you have to spend some time to build a system. The reason is you typically receive the lenses from a lens design software, the mechanical parts from a CAD model. Then you have to bring them together. In 80 to 90% of the cases, there are inconsistencies which you have to remove, which are very important, of course, for understanding the system. Then you have to get the scatter models, the coating models. Finally, you have to verify that. So not surprising, this system build can take a long time, sometimes really more than 50% of the Straylight analysis, if there are inconsistencies. Then you have to prepare the analysis, get the critical illuminated objects, do the importance sampling, and make things automatic. Because in many cases, you have to study lots of different situations, sometimes hundreds or thousands. And this can be done very, very conveniently, of course, with Python, because it's a programming language. Then you have to do the job. That means simulate, aggregate the data, perform path analysis, and analyze. And finally, you will have to write a Straylight report. And this still may take another few days, up to maybe 2 weeks, depending on the complexity of the system. So that's a little bit sketched here. I won't go into details. Let me, at the end now, talk a little bit about the input data, because it's often a real mess. The predictive power of Straylight simulations is quite high, but it is limited, of course, by the quality of the input data. And measured data are often not available. One reason is that, for instance, if you're purchasing such a filter, the supplier typically provides you with a transmission data for nominal angle of incidence and for the nominal wavelength. But if you want to know the transmission or reflection of this filter in the mid-infrared, most likely you have to measure yourself. So the other thing is, optical properties may dramatically change over wavelength. So something which looks black, like this black anodized aluminum in the visible, is not black at all when you go to the infrared. So you should definitely perform measurements, and educated guesses are dangerous. So I would say more measurements are needed. And let me now summarize. I have given you a brief introduction to Straylight analysis and Straylight quite generally. Then I introduced our software RayJack ONE, and it was applied to a simple Straylight problem. We have just touched the tip of the iceberg. There is far more to talk about, both with respect to Straylight and, of course, with respect to RayJack ONE. Feel free to contact us if you need more information or if you need a trial version of RayJack ONE. Thank you very much for your interest, and here is my contact information.